they have sometimes problem with that. Okay, so today what we'll do, we'll learn different ways of calculating dynamics in quantum mechanics, and actually two of these ways we have learned before. So I will just do a quick revision on these two ways, and one is this Schrodinger picture. Schrodinger picture, another is Heisenberg picture. And the third is Dirac picture. So what is the main, of course these are just three names, you know of course nothing from just the names. So Schrodinger picture is where the state evolves. Here the operator evolves, and here both evolves partially. And I will tell you, let me just tell you in a very brief manner what do I mean. So this is useful for problems which can be splitted into these two parts like perturbation theory. And here I evolve the state with H0 and operator with H1, or vice versa. Either way I can do, okay, or opposite. So you will see why do such a strange thing. You will see they are useful in certain contexts, okay. So this is the basically the whole class. What I will do today is this. If some of you have good comment on Schrodinger, all this Schrodinger dynamics, Heisenberg equation of motion that we did in the previous semester, then you basically know everything what I am going to tell you today. Okay? This is so simple. But then we will do one more thing which is a little tricky. That is the problem of solving this. Yes.
One Hamiltonian, one way state evolve, another Hamiltonian.
Yeah, so I will no. So I will say, see, what is this e to the? So okay, so that means you forgot everything. Okay, this is the signature of that. So if you remember any of this, you will remember that in Schrodinger, the state was evolving as e to the power iht. In Heisenberg, it is going as e to the power iht, some a operator e to the power minus iht. So here I am going to evolve the state with the h0 part and the operator with the h1 part, right? And why I can do that? Because the whole point of all this thing is that the only physical observable, the physical object is expectation value. Okay? So if the physical object is expectation value, then what I can do with the state or operator, it doesn't matter, as long as the physical object is intact, right? Because at the end of the day, this is what I want to calculate. Okay? Now whether I put the time dynamics here or I write it like here, it doesn't matter, right? This is basically Schrodinger picture, and this is basically Heisenberg picture. And what we'll do in Dirac picture, we'll split this time dependence, which means the psi will be also function of t. Let me call it psi tilde. O will be also function of t. Let me call it O tilde. But the psi t evolution will be with h0 and ot evolution will be with h1. Why I can do that? Because this is an additive form. So e to the power minus I h0 plus h1. So I can split this, take one of them here, one of them there. Okay. This is the whole lecture. Okay. This is the whole lecture, and you are done right now if you are fully familiar with this Heisenberg and Schrodinger. Very easy lecture today. Okay. Okay, everybody got this idea? Okay. We can go home right now if you got this idea. Okay.
Sir,
Online audience?
sir, can you turn off the light, like the front one? It's too much shining on the board.
Is it fine now?
Yes, sir.
Okay. So did you all get the idea, online audience? The outline that what is going to happen?
Yes, sir.
Okay. So now another thing I will do today is deal with this solution, where the t is explicitly time dependent. Okay. So now this is going to be tricky, as I gave a brief outline last time, because I told you that if your h at particular time t is commuting with another time, then it is fine. Then they have all the same basis, right? Then you use one basis, they are simultaneously diagonalizable, and then you in that basis you can solve this equation. But if that is not the case, then it is a problem. Then you have to define something else. Then you have to do something else about it. And we have to now learn all these things because now we are entering in a chapter of time dependent quantum, where the time dependent perturbation theory basically, and the Hamiltonian is explicitly time dependent. Okay? So this is basically what we are going to do today. This is the whole summary of the class. Okay. So let's start with Schrodinger picture. So Schrodinger picture, I had this. I'll just do some quick examples. These are examples that we did also in previous semester, so that's why I'll go through it quickly and show in some simple problem that how these two pictures give you the same result. Okay. So you want to solve this. And let's say it's time independent, okay, for the time being. So psi st, we know the solution of this equation. It is e to the power minus I h t by h bar psi s 0. Okay. This is similar to the translation operator. That's how we constructed in the previous semester. Like space translation operator, this is a time translation operator. In space translation operator, you had this state at x plus a was related to e to the power minus I p dot a by h bar psi x. Okay. This is similar to that. Okay. So now let's try to understand that what matters in any calculation and what do I need to do that. Okay. So what do you do in Heisenberg picture? We want to, let's say, calculate, the end of the day we want to calculate some operator, let me call it a, right? Okay. We want to calculate this kind of object, an expectation value as a function of time. So you can write it as some at. Okay. Now the simple idea is, so let me call this thing as ut0. So I call this thing as ut0, ut at t0. So this is just a definition. So ut at t0 is given by e to the power minus I h by h bar t minus t0. Okay. So what do I want? So I want this quantity. So this is basically psi 0 and I can redefine another quantity called h. So basically I have now shifted. So in the Heisenberg picture, now what I'll do, I have now shifted. So this is Schrodinger. Okay, this is just Schrodinger at time t, just like this. Okay. So instead now I have a Heisenberg, which is okay, and that is nothing but the same as this. Okay, so you can easily see this without any, we are not losing anything. The expectation value is the same, except what I am doing, I am saying the operator is time evolving, not the state. The state is frozen, state is 0. This is basically nothing but your active and passive transformation, like the one you learned in classical mechanics. Whether you transform the object or transform the coordinate system, right? Here you are, it's similar to that, whether you transform the state or transform the operator, such that the measurable is invariant. Okay. Here. Okay. So notice this kind of dichotomy you have in quantum mechanics, not in classical mechanics. Okay, I'll make the connection with classical mechanics clear in a moment, but let me just state that. You have this because in quantum mechanics there are two objects. One is an operator, another is a state. In classical mechanics, the operators are the states, like they are the same thing. So you didn't have these two different things. Okay. So let's just write down the. So okay. So now we know this is the differential form of this equation. This is the differential. So this equation 1 is the differential form of equation 2, right? So they are basically both telling you the same thing. So now this is not a differential form. So what is the differential form for this? So I can work it out by taking derivative. Okay, and that derivative will be d dt So I have to just do three terms. So first it will act on this chain rule, basically act on this, and then it will act on this. So the first term will give me I by h bar e to the power I h t h a h. So a h, let me call it a h 0 minus simply because if you take a derivative, okay, there is a h bar everywhere. If you take a derivative, it will be come with a plus sign, and if you take it here, it will come with a minus sign, right? So what is this quantity? This is nothing but 1 by I h bar a h t, because if you take it out, it is just a h t h, assuming h is time independent. Okay. So the time derivative of the Heisenberg operator is, this is something also we did in last semester. Okay. So equation 3 and 4 are equivalent to equation 1 and 2 in differential form and in its whole form, right? So if I have to write the operator everything in terms of this, I have to just do this much. And we also know that this is the equation of motion that corresponds to quantum, that corresponds between quantum and classical mechanics, because the classical equation of motion is nothing but the Poisson bracket form. Okay. And we know the correspondence principle tells you when I go from classical to quantum, I replace the Poisson bracket by a commutator and divide it by IH bar. Okay. So this corresponds naturally because in classical mechanics only what we have are variable, and variables are equivalent to measurables or operators in quantum mechanics. There is no correspondence with state in classical and quantum. That's why you will get an equation motion in terms of the states, but that equation of motion will give you the same thing, and there that has no equivalent. Okay. So these were basically the two ways to calculate dynamics. Either you transfer the dynamics to operators, or you keep the dynamics to your states. Okay. So now let's just quickly see once that how to use this. All these things you know. This is just a revision. Okay, everybody is clear up to this? Yes. Online audience?
Yes, sir.
Okay. So now let's do a, just to show that these two are equivalent, let's just see that how the calculation goes. So let us say I know this Hj is equal to Ejj. So this is we know that in order to calculate the dynamics, you need this Heisenberg, this Hamiltonian eigenstates, and then that makes the whole thing easy. So I have an arbitrary state which is Cjj, okay, and an arbitrary operator which is Jj prime. I can write it in this basis. Right. So now I want to calculate the dynamics. Society. We have done these exercises explicitly for many different problems like particle in a box and all this. So I have to do e to the power minus IHT by h bar psi 0, and this is cjj, so it will be eventually become e to the power minus iht cjj. Okay, this will act on this and give me so this is my new j, so I call it cjtj, okay? And this cj is just cj0, and we know that we have learned this explicitly, that this is equivalent to saying that if I write this psi t, this is basically you have this one with a phasor, right? Another with a phasor. See. Okay, so if I expand this, this is like a, each of them is like a phasor, the coefficient, and this phasor is why it is a phasor, because these are all, this sum square is 1 and it cannot never exceed 1, so you can imagine it like a, the only thing is varying is this angle, right? Only the angle because is varying because of dynamics. So what the dynamics does, it basically rotates this thing at different rate, and how fast it rotates is given by the EJ. Right? So dynamics is nothing but a bunch of states, is a bunch of eigenstates, energy eigenstates, whose phase factors, the prefactor of the phase factor they have, they are rotating at a different rate, given that is determined by this eigenvalue. And when you want to ask the question, what is the state at a particular time, you basically take a snapshot at that time instant. Okay. And basically, if you don't do any measurement, that is how it will go. Of course, if you measure, then it will collapse into one of those. Okay, this was basically what we learned explicitly at the picture of dynamics. Everybody is clear about this picture, right? Okay. So this is the problem of quantum dynamics. So now I want to calculate this quantity, psi t a psi. Okay. So how will I calculate it? I will just, so I know this thing goes like this. So basically I'll have a cjt prime, j a j prime. No, not cjt prime. Sorry, cj prime t. Okay. Cj prime t, and it will be star here because it's commutator, it's conjugate. So then I will have cj j prime, j and j prime, okay, which I can rewrite it as cj0 cj j prime 0 by using this relation e to the power I ej minus ej prime, okay, and this matrix element a j j prime. So basically, your calculation of any such expectation value, it boils down to knowing these CJs and knowing these eigenstates. That's it. Oh well, one more thing: the matrix element of A in the JJ prime basis. Okay. Once you know these three things, which are very easy to calculate, as we have done in many different examples, then this is what it will give. Okay. So now this is the operational process. This is the operational process. If I give you a problem, for example, a spin Hamiltonian or a particle in a box or something, how do you calculate this kind of expectation value? Okay. Now let's do that in Heisenberg picture. So what will happen in Heisenberg? So this is Schrodinger picture. So now we'll do it in Heisenberg. So what do we have to do? We have to calculate the AT. Now I have to calculate this instead of this. Instead of this, I have to calculate this. Okay. So I will just use a resolution of identity twice. So basically I will do okay, and that will give me same thing, because this will act on this e to the power I ej minus ej prime by h bar t a j prime, and there will be still a, what did I do here? Yeah, there will be AJJ prime will come out and there will be still a JJ prime. Okay. Okay. So now I calculate the matrix elements psi AP, and then that will give me psi and j. This inner product psi and j is basically your Cj. Okay. So what do you get? Cj prime. And these two are basically the same thing. Okay. So just to show that how it is operationally the same thing. Of course, that doesn't mean like, so then still what do we need these two things? Various reasons. One is, first thing is that sometimes it's easier to do a particular calculation in one way compared to the other, and you will see some of that. And other deeper reason is that this is, we need the Heisenberg way to make a connection with classical mechanics, because in classical mechanics there is no phase. Right? So this is the more natural way to represent something, because you know that classical mechanics is a limiting case of quantum mechanics, right? Is emergent from quantum mechanics. Okay, so let's now do one example, one more a precise example. So this is what so now this is already an example. Now it's an example of example. So this reminds me a joke. So once there was a, so when I was I think, I don't remember exactly where this happened. I think in TIFR somebody was doing a project, and in string theory or some very obscure topic, not like yeah, so more mathematical and theoretical topic. I think string theory he was doing a project. So but in those subjects people are very abstract, usually very abstract. So then he was talking about some example. He was talking about basically some Hamiltonian, this Hamiltonian, that Hamiltonian, and all that. So then one experimentalist audience asked, "Can you give me an example?" Okay. Then the speaker said, "All these were examples." So what is a theory then? The theory is more abstract, something that for much more generic. So whatever. So this is an example in that sense. But now we'll do one more example, which is more like example in the sense of, so what was theory? The theory was that these two are equivalent, the abstract statement. The example is basically how to calculate it. Now example of example is how to calculate it for this Hamiltonian. Is dot d, some spin in a magnetic field. Okay. So let's do the example of example. Okay, so let's say I have a spin half. Let me write it properly. This board is much better. Somehow a board or duster, the whole thing is much better in the sense that it doesn't produce much dust. But the main campus board is also good in the sense that somehow the when I write on it, it's brighter. This is not so bright, but that could be because of the lighting also. But this produces less dust, which is what I like. So let's say the example is, write it properly. The p factor is minus GE by 2m is dot p. So this is basically the problem of spin precession. Spin precession. Maybe the spelling is wrong. I have a spin and I have a magnetic field. Okay. We know the actual motion, what happens. We know it pictorially also, I can write it. This is the block sphere, and if it's pointing there, the spin will, the state vector will precess like this. Right? This is what we learned. So how do we get this? So if my B is pointing in any direction and I take that to the Z direction, so then H is and energy levels are. So I can diagonalize this Hamiltonian. This is a 2 by 2 matrix SZ with plus and minus. This is already diagonal. I don't have to do anything. This is a minus, so it will give me minus GE8 cut B by 4M. Okay. So your H is SZ plus minus E plus minus Sz plus minus. So you get. So now I define a quantity called h cut omega, which is Ge h cut beta by 2m. Yeah. So h is basically omega sz. I just pack all the p-factor inside this omega. Okay, and there is a reason to do that also. You can see that omega has the dimension. Call it omega. It has the dimension 1 by time. Okay. So the Schrodinger picture will do the following. So I want to calculate. I start with a state which is C up dagger plus C down down, and this could be 1 by root 2 if you want. That is the kind of state we dealt with before, and I want to compute the psi t. So I add this e to the power minus I omega sz t by h bar on this psi 0, and I get with up. This is an eigenstate of this. Sz is up is an eigenstate of sz with plus h bar of eigenvalue. So what I'll get is e to the power minus, it will h bar by 2 eigenvalues. I get I omega t by 2 okay. So if I take my C up to be 1 and C down to be 0, that has to be true because sum square is 1. So then it will remain in C up with this, as we know, because this is a stationary state. Okay. Now I can compute something else. I can take this to be 1 by root 2, 1 by root 2. C up, C down, 1 by root 2, which is a superposition state plus x and all that. So then my psi t will be just, I will just get this 1 by root 2, 1 by root 2. So I will get 1 by root 2 here, 1 by root 2, and I can compute some kind of a expectation value, which is Sx. And check this calculation. I am not doing this one step. So you have to just write the Sx operator and write the psi t here. Okay. We have done this kind of calculation before, and I get h cut by 2 cos omega. The Schrodinger calculation is easy. That is something you have done before. Okay. This is also what we expect from classical intuition, because we picturize this problem as a split precision problem. Okay. Everybody clear to this, up to this? Online audience?
Yes, sir.
Okay. So now let's see what do I do for the Heisenberg picture. Again, I will do nothing. I will just plug into these formulas, and so we have to first write down the equation of motion. So what do I do? So we have St omega is t by h bar is 0. So this could be the vector spin, and now I can write down each of this component. So I can compute that dsx dt, and as you know that this is nothing but sx h by I h bar. Okay. Now h is basically sz, so you use the commutator and you get minus omega sy. We know sx sz commutator will give you sy. Okay. Now check the factors, omega, minus, and all those. Okay. Similarly, if you do dsy dt, you get omega sx. So this is basically a pair of coupled differential equation, and this is basically nothing but the equation of motion of classical spin, because this is, when you write this ds dt as a vector form, this is minus omega s cross z. This is what you expect in the classical equation of motion of a classical rotor. Now I can solve this. Now this is a coupled differential equation. So I can plug this sy here. I can take double derivative here. Okay. And double derivative will give me d2 sx square dsy dt, and this is just sx square, omega square sx square. It's basically an oscillator. And you solve it and you get 1 by 2 cos omega. Okay. Same answer, but you can see it's much easier, right? It's in this way you have to do much more lengthy calculation. Here you just have to write these two equations and solve it. Okay? At the end of the day, you want the same thing. You want the expectation value as a function of time, and in some problems it is easier. In certain case it is easier, not always. Okay. Okay, everything is clear up to this, local and online.
Yes, sir.
Okay, so basically this is what I wanted to tell you about what we learned already in previous semester, but now I will go ahead and talk about a third way. Well, before I talk about the third way, let me start. Okay, before I tackle another issue, this is basically the time dependent Hamiltonian. It is useful to know that issue because that is where the third way is going to be particularly useful. Also, I will not do an application of the third way, but today I will not do an application of the third way today, but the whole time dependent perturbation theory, I mean a bulk of it is basically that. So that's what we will do eventually. Okay, so now consider the case that H itself is time dependent. Okay, what do I do? So notice that my original problem was this. Now, of course, I have to first start with the differential form for a reason that I cannot say that what happens to far apart term if they don't commute, but we'll see in a moment. But let's just start with this equation. So this is what I want to integrate, and if ht was time independent, then all I needed is this. Okay. Now let me not mark it. Okay. So what did I do here? So in this is my ut. So ut, this is my ut. Okay. Now what I can do, I notice that now I cannot do a full time evolution because there is no way to do this. I cannot put a j here, right? I cannot put this resolution of identity there like before because this j is could be an eigenstate of ht at time t, but need not be an eigenstate of ht at another time because they don't commute. So now I want to formulate this problem in a more general way. Okay, so let's say what are all the things I can tell about this problem. So first thing, notice I expand this quantity. So ut is basically u t to 0 because it is from t to t naught as I defined earlier. So I defined an infinitesimal quantity that takes you from t to t plus dt, the small distance. So this is basically that I can expand as, notice everything is time dependent, plus order dt square. So then this object, now I also know that composition rule of time translation, which tells you the operator that takes you from here to here can be decomposed by operator that takes you from here to here and then here to here, right? Time operator. So it's simply saying u t plus dt starting from a t naught is equal to u So this is T naught, this is T plus dt, and this is T. So U T plus dt T U T to T. Okay. So now I can rewrite, I can rearrange all these things. I know what is this. So if I rearrange this, U T plus dt T naught minus U T T naught. I just wrote down this expression. I bring it here. That will give me minus I by h bar ht dt U T to T naught up to that order. Okay. Now dividing both sides by dt and taking dt goes to 0, I get this. So I divide both sides by dt, and then this is gone, and take limit dt goes to 0. I get I h bar du T to T naught dt ht u T to T naught. So what did I get? I get an equation of evolution of the u itself, right? The u is the operator that takes you this from one time step to another time step. Okay. So why do I need that? Because I need that now to integrate this equation to find what is the ut will be, and this has to be done with great care, because this t has to be in between these two, in between this t to t naught, otherwise I cannot write this kind of a decomposition. Okay. So let's first remind that if your ht is equal to h, sanity check, okay, there is no time dependence, then this equation is trivial, then it is the same as before, and your solution is just this. You can also check by plugging in the solution. You can just plug in this solution and see that. Okay. Now it is also simple. Yes. Yes. Sorry, what cannot be done? No, which step are you talking about? This step. This step. What is the problem in that step? All I'm saying, I'm going from T naught to T and T to T plus dt. So that is same as T naught to T plus dt, right? It's a general rule of any Hamiltonian. It's a general rule of composition rule of time translation, right? What is the problem with that? It doesn't matter, because it is true for any u, right? What is the job of a u? The job of u is to take you from one T naught to T, right? Now whether you write the u in this form or not, that's a separate question. But it's a composition rule of u, right? You go from point. Now if I say, if I have a u that takes you from T naught to T and then T to some T1, right? T1 to T1 to T2, right? Now this is always true that your T2 to T0 u is the same as taking first T1 to T0 and then T2 to T1. This is always true, right? Irrespective of anything. Okay. Okay. Only thing you have to make sure that T1 is in between T0 and T2. It is not a point which is outside. Okay. Actually, technically, mathematically, it is still true, because you can still do that. But the job of this u, so the u operator will, but we don't want to physically go back and forth in time, basically. But also you might have to do it in some other context. But this is generally always true, right? It is true for not just time translation, even any space translation. The space translation operator that takes you from this point to this point, and another that takes from this point to this point, then that operator that takes you from here to here, it should be equal to these two, right? This has no physics or nothing. This is just basic things, right? So now I am using this here, right? And then what I am doing, I am saying that this quantity I have already so where is the time dependence is taken care of? It is taken care of in this step. I am just saying this ht is a function of time at that instant dt. Right? Then I am throwing away this all higher order terms which should be there. Right? So that is where I'm handling this time dependence of this problem. Because this dt is so small, this ht is not changing over that period. So that is why I can just write it like that. Right? So I'm plugging in here and getting a differential form. Right? And this is what, let me tell you also the gist of the idea, what are we going to do. We are going to do this time evolution, t to t1. When the h was not a function of time, we just did e to the power minus iht. Now we have to do this. We have to decompose it into small pieces and do e to the power iht for this, e to the iht for this, and e to the iht for this, and hope that this interval is so small, not hope, I mean this interval will be taken to be so small that within that small interval, the ht doesn't change, right, in time. So then you can write the same time evolution. You just have to make sure you multiply them one after the other and in a proper order. Proper order such that this time is after this time, this time is after this time, this time is after this time. So this is the gist of the, yeah. So this thing is called Trotter decomposition. This is the whole point. This is what we will do. Okay. Okay, this is the end. This is again. This is what we'll do. Again, I am telling you what the conclusion of this whole lecture is. Okay. So now I write a general solution of this equation when ht is function of t. So then the general solution of this equation is e to the power. No, this is the case when ht is h. So then the general solution is minus I by h bar 0 to t0 to t ht prime dt prime. Okay. This is the general solution, always true, but this integral you can explicitly calculate when ht is t independent, right? Then it becomes simply e to the power minus I by h bar h, okay, h times t. But now, as I said, now you have a situation where ht doesn't commute with ht prime. Okay. So now the strategy to solve this equation will be to take your whole time evolution and split it. Okay. N intervals such that your t0 is t1 to t2 and t is equal to tn. Okay. So how will you solve? So you will solve it by saying your del t is basically ti plus 1 minus ti. They are all uniform interval, so that is t minus t naught by n. So you take n going to infinity, that means del t is going to 0. Okay. So then what do you have? Now for take one such interval, I to I plus 1. Okay. So for this interval, I can write this expansion plus order delta t square. Now in this interval, this is equivalent to okay. In this interval, these two things are same, right? Up if delta t square is small, because I have chosen the delta t to be small by taking n going to infinity. Okay. So now my time evolution is this. Now I use this rule again and again, right? My time evolution is nothing but t to t naught u t to tn minus 1 tn minus 1 tn minus 2 ut1 t0. Okay. I go from here to here, then I go from here to here, go from here to here, and all that. Okay, this is my time evolution, such that at each instant, each of this interval, it is satisfying this equation with a h constant. Right? That is the idea. So that's why you can write it that ti is constant for this interval, not for the next. So there is a difference between next two separate intervals. That's why I cannot mix them, and I cannot shuffle them either because they don't commute. Right? I cannot move them here and there. So this quantity is called time ordered. This process is called time ordering. This decomposition is called Totter decomposition, and there is a notation for this. It is given by. So this is the solution of this equation in general for h independent, right? When h is time independent. So I am writing this t, but this is time independent. Right? This is the general solution for this problem. For this problem. But for this problem, this has to be the solution because I know how to solve it for one given interval, and I cannot connect two different intervals. So I have to solve it for each interval. I have to know the solution at each interval and product them. Right?
Sir,
And yes, just a second, let me write the solution. So the solution is in this form. Okay, so this is basically this solution is written like this solution is written like this with a t in the front. Just to remind you, this is actually this time ordered product, not the same as this, just an integral. Yeah, tell me.
so are we assuming that the h of t would be constant for a particular interval, small
Yes,
interval?
yes. I'm assuming for a given interval, if it is small enough, then the ht is constant because t is so small. Yes,
Okay, sir.
and that is always true if n is going to infinity, and del t is going to 0.
Okay, sir.
Yeah, this is basically, there is nothing mysterious here. This is basically Riemann sum. This is how you handle Riemann sum, right? Yeah.
So the difference between time machine and time independent is time ordering.
Yes. Here you have to do time ordering. There is no need to be careful about that, right? Because these two. So okay, let me be careful. It is not just time independent, time dependent. It is time dependent with non-commuting. Right? This is also time dependent. So this equation is generally true. Okay, this let me make this clear. We derived this equation for a generic time dependent Hamiltonian, right? We derived this equation for that. This is always true. It doesn't matter what is what. It is just dt is tends to 0, so this is always true, right? So a generic time dependent Hamiltonian can be solved by this, right? When the ht is just a ht, just a generic ht. Now this solution is not the correct solution when this h doesn't commute at different time, right? For obvious reason, because you cannot just integrate it over all the time, right? So this equation is itself different. The basis, etc., solution, everything is different from each time step. So what you can do, you can totalize. This is called totalization. You can totalize means that you can cut your time interval into pieces, and you say each piece is so tiny that within that piece, this h is a constant, or even if it is not constant, it is not a problem. It's just a function of t. And then you write down the solution in this product of these each pieces, and you are very careful to never shuffle this order, right? When you are doing a blind sum, and I will show you in a moment why this will matter, because how do you actually evaluate this kind of integrals? You evaluate it by expanding it, right? And then this commutation relation comes, right? So let's just do that.
So both are like time dependent solutions, and when there is no commutation relation, we use time ordering.
Yes, and now notice it is not yet very useful. By the way, it is not yet very useful. I just told you a very complicated way to represent the problem. Okay. Now, what do you do actually operationally? There is no. It's not a solution. It just tells you a strategy to solve it, a correct strategy, right? So now let's do something that will tell you actually how to do this.
Sir, can you once repeat the T notation?
What notation?
T at the last.
Yeah, T notation is nothing but multiplying these each intervals, right? So each of this is basically this. This is the T notation.
Okay.
Okay. So I will show you in a moment an alternative way to represent the same thing, which is operational. This is not an operational solution. This is a conceptual solution. Okay. Now let's. Okay, time is up actually. Oh my God, how fast? Okay, so let me just tell you the operational solution. So I want to integrate this equation, right? du t to t naught dt minus I by h bar h t u t to t naught. Okay. So I can integrate it. So what is my goal? My goal is to solve this equation for a arbitrary case. Right? Commute or not commute, a general case. So let's say not commute, the most general case. So I have to integrate this. So let's integrate this. Okay. So this integral I have to calculate now. So then this is simple. This is a whole derivative times dt. So it is just du, and integrating that will give me u t to t0. Okay. So t0 to t. So t0 to t. Okay. So now this side of the integral is the tricky part. So okay, so let me write it explicitly. So this is dt prime d dt prime u t prime t0. I have to integrate this, right, from t0 to t. So what is this? So this is a whole integral. So it is u t t0 minus u t0 t0, right? Because this is a whole derivative. So what I have to calculate is this, and this is equal to minus I by h bar t0 to t h t prime u t prime t0. So this is what we have to solve. Now this is obviously 1, right? T0 T0, right? You are going nowhere. So what you have to solve is basically u t t0 1 minus I by h bar t0 to t h t prime u t prime t0 dt prime. Okay. Now this is a classic problem. This is a classic problem where this object appears in both sides. Right? These objects appear in both sides, but you want a solution for this. Right? So this is what we will see how to solve. By we'll use the following simple strategy. We'll just put a t prime here and make it a t double prime. So then I know the solution for t prime to t0. Then I plug it here, okay, and get the solution from t to t0. Right? So we will do that iteratively. You see the issue that I want to have a equation where I have an unknown in both sides. So we will solve it iteratively. So okay, I will stop here. So what's the time now? Yeah, it's time is up. And I will express the solution of this equation in terms of a series, because this ut can be solved also by the same equation, and that will give me another ut, and that can be also solved by the same equation. Right? You get the point, right? Online audience, did you get the point?
Yes, sir.
Yeah. So what do you get? You get a power series in H. So if I replace this by this, I'll get this 1 minus H integral form, and then inside this also 1 minus H integral form, right? I get a power series in H. Okay. So now comes the perturbation theory. Now that it is a power series, then I can say if I can truncate that power series somewhere. Right? So that is what we will do. Okay, I will stop here. The idea is this. This is still not a solution, by the way. But it's a hope to solve it, where you can. So it becomes an infinite power series because this u is also following an equation like this. So you put that 1 minus h, then that will have another u. So then you put another 1 minus h, right? and you keep doing that. So you get a power series in H. You will get a H term, H cube term, H to the power 4 term, and so on. Right? So then what you are going to use? You are going to split your Hamiltonian into two parts. One part that doesn't have time dependence, another part that has time dependence, H naught and HT. So then you say H naught I can solve anyways, there is no problem, I can just integrate it. The HT is the problematic part, and the HT part, so then you will say this, I have a HT which is H naught, which is not time dependent, and HT. Or you can say, okay, this is both time dependent, but this part is the commuting time dependent, this is the non-commuting time dependent. This is the problematic one. So then you can put an epsilon and truncate that power series. Okay, that will be our game plan for the whole time dependent perturbation. That's again the summary of whole time dependent perturbation theory is that. Okay, so this is what we'll start from here, again from this idea, and basically talk about the Dirac picture, and finally we'll move on to time dependent perturbation theory. Okay, it's very simple, and you can see that how you are basically just finding what you can or cannot do, that's all, and then you are using what you can do in an operational form. Okay, questions, online audience? Is it all clear first of all? Okay, perhaps nobody is there. Okay, that's all for today then.